imagine someday building a home robot that can perform a variety of tasks in your kitchen, then it becomes a lot more than just a perception problem. Then you really need to be able to learn the individual manipulation skills. And you need to be able to generalize very broadly.
Hi, I'm Craig Smith, and this is Eye on AI. Today, I talked to Sergey Levine, an associate professor at the University of California, Berkeley, who does research at the Robotic Artificial Intelligence and Learning Lab at the university and is pushing the boundaries of what AI control of robots can do. Sergey talked about some of his recent work in reinforcement learning and the aggregation of data sets from robots around the world to help train a model that can generalize across different kinds of robots. It's exciting research into embodied AI, bringing the transformative technology out of the computer and into the real world. I hope you find the conversation as fascinating as I did. So, Sergey, could you start by introducing yourself?
So I'm an associate professor at UC Berkeley. I previously did my PhD at Stanford, and I also spend one day a week at Google, Robotics at Google, where I also work on robotic learning. My research concerns, of course, robotics, but also many other related techniques in machine learning, reinforcement learning. Lately, my group has also been doing work on various things related to reinforcement learning for language models, computational design, things like this, other aspects of decision making.
You know, everyone's talking about world models and they're combining world models and language models. Are you working on world models at all? What's your view of that?
Yeah, I guess there are a few things I could say about it. So generally, if we want to control robotic systems, there are a number of ways that machine learning can enable that. One very simple way is imitation learning. Imitation learning amounts to taking demonstrations, typically provided by a person controlling the system, and then imitating those demonstrations to try to produce an agent. And that can work for robots. It can work for lots of other things. Arguably, language models are just giant imitation learning machines because they're imitating how humans generate text. There are lots of other ways to do it. So a world model is essentially a dynamics model that represents how the environment will evolve in response to the agent's actions. And we can learn that from data too. Typically, in reinforcement learning, that's referred to as model-based RL. So model-based RL means you train a model of how your environment behaves, and then you use that model to figure out how to act in the world. And it's a very old discipline, actually. In fact, the first learning-based control methods before model-free RL became such a popular thing were actually model-based RL methods. Some of the earliest neural network control methods actually use dynamics modeling. And again, there are a million different ways to instantiate this. You could instantiate dynamics models or world models by, for example, taking image observations and doing video prediction. You could also instantiate them by learning non-reconstructive representations that sort of, roughly speaking, capture the state of the system without necessarily grounding it back into pixels and then predict that. So there's a lot of different approaches for doing this.
Recently, I've been talking to Wave about their Gaia model, and I've seen the videos, but they have that model built into a controller, connected to a controller to operate a autonomous vehicle. What's different about that structure or architecture from what you're working on with reinforcement learning?
I don't think there's that much I could say about it because I don't know how their system works. I mean, I've seen the public material, the same as everyone else, but I don't really have any insight about the details there. Maybe one thing I would say, though, that most methods for learning-based control don't necessarily need to predict the raw pixels that the robot's camera will observe in the future. That is one way to do it, and there's a lot that can be done with that. But I think that the more significant distinction is actually how well we're able to utilize data to then produce more optimal decisions. And going through prediction is one way to do it. And you could predict pixels, which is what video prediction models do. You could also predict outcomes or rewards, which is what value functions do. At the end of the day, they are actually not all that different. And maybe a bigger distinction as to whether you can get a system that really works in the real world is what data it's trained on. For example, if you want robotic manipulation systems that will, actually work in broad open world environments, you need to train them on data from broad open world environments. So a lot of what I'm actually concerned with in my research is how do we develop learning-based control techniques that can use large amounts of data, and how do we figure out what data sets we can acquire to get really generalizable, in my case, often robotic manipulation skills, but also robotic navigation skills and things like that. Systems for manipulation for things like warehousing, oftentimes those problems can be, to a large extent, reduced to perception problems. So if you structure your environment in the right way, then as long as you're able to detect where the objects are, then you can use hand design strategies for tackling that. That tends not to work so well if you want to take the robotic system into more open world environments. Like if you imagine someday building a home robot that can perform a variety of tasks in your kitchen, then it becomes a lot more than just a perception problem. Then you really need to be able to learn the individual manipulation skills. And you need to be able to generalize very broadly. So maybe one thing that I could discuss here that could be relevant is a project that we actually did recently. This was actually a collaboration between Google, Berkeley, and several other universities on trying to see how could we get robotic controllers that actually generalize across different robot morphologies.
Mhm.
And that's actually really important because if a lot of this comes down to data, then then it's very difficult to get the kind of breadth and diversity of data from a single robot that can allow the kind of broad generalization that you want from a home robot. But if you can pool data from lots of different robots, then maybe you can actually get that kind of coverage. And furthermore, if you can actually do that and you get a system that generalizes across robots, then you get something really cool, which is, in principle, someone could put together some new robotic system and then plug this kind of robot brain into it and immediately get something that can control that robot. Now, the work that we did so far on this wasn't really that concerned with building better models so much as just getting this diverse data set and just applying kind of standard techniques that we'd already developed in previous works. And that actually worked decently well. So this project was called RTX, and the idea there was that we got data from, in the end, it was 34 different research labs.
Mhm.
Google was one of them. Berkeley was, actually, there were 2 labs at Berkeley that contributed data to this. And then we trained a model on this to control, to perform basically language condition manipulation tasks. So think like you give the robot an instruction, pick up the tomato and put it in the bowl, and the robot is supposed to do that. And then we took this model and we handed it off to the different labs that contributed data and had them test it in comparison to whatever model they had for their research, basically trained on their own system. And the multi-robot model actually was, on average, about 50% better in terms of success rate. And that's actually pretty interesting because this was competing with whatever each lab's individual system was. And presumably, if they're good researchers, they built something that works pretty well in their system. Now, this was actually an imitation learning approach, language condition imitation. I think that whether it's imitation or prediction or world modeling, I think many of those techniques could be made to work. I think the high order bit here that I want to get across is that by actually getting this data set, you could actually get a system that could plug into all these different robots and actually get good results out of it.
That's fascinating. That model was being trained on data sets from all the various participating labs.
Yeah. So in these experiments, we were not testing whether it could generalize to a new robot. That's a very exciting frontier for this, but that's still in the future. This was just trying to answer the question: if you include data from the other labs, does that one lab's robot get better? Now, of course, if you're sort of in the minority, if you're one of the groups that contributed a relatively small amount of data, you would expect to see comparatively more benefit from everyone else. Interestingly, actually, even the majority contributors saw a lot of benefit. So probably the largest data set at about 100,000 trials was from Google's own robot, the mobile base that we used in a lot of the robotics research there. And with that system, we were able to actually test it on various. We have this kind of test suite of difficult queries. They're actually meant to be queries that are that require synthesizing, pre-trained knowledge from the web, as well as good instruction following ability and so on. So they require spatial reasoning, things like that. And on the hardest test, we actually saw a 3x improvement in performance over just using the Google data set. Now that's actually, in my mind, pretty profound, because the Google data set was very carefully curated, collected, by basically professionals that were collecting robot data. And the fact that including all these additional sources of data from a long list of academic labs actually led to that much improvement really suggests that there is something kind of magical that happens when you combine enough data from enough different sources. Yeah, so for these experiments, we were actually passing the model around.
Okay.
The data set is public now, so anybody could take that data set and download it and train their own models. And we actually have an ongoing effort at UC Berkeley that my students are, for that initial experiment, it was just the model weights.
Hmm. That's fascinating. Just the model weight. So the architecture of that model was being replicated in each lab. They weren't using their own model.
Correct. Yeah. So
Yeah.
it was exactly the same model with exactly the same weights that had to drive all of the robots in all
Yeah.
the locations.
Yeah.
And
Oh,
that is actually, if you think about it, it's a very non-trivial thing, right? Because all the model gets to see is what the robot perceives through the camera, and it has to figure out that, okay, now I'm driving a UR10 industrial robot versus now I'm driving a low-cost Widow X robot, or now I'm driving a Franca or
yeah.
the Google robot, and adjust the controls accordingly.
When I was at the lab, as I recall, that you had robots that were networked. So the learnings from one
Mhm.
were updating a
Yes,
central
yes.
brain, and that then was controlling the other robots. So each robot. Have you done broader experiments like that?
Mhm.
Very much like this.
Yeah. I'm glad you asked that. So this was a lot of what we were trying to do for over the last 5 years, actually. And in some ways, this multi-robot training effort, it's kind of partly it came about kind of in acknowledgement of the limitations of this kind of arm farm approach. So getting lots of robots in a room is great if you want to prototype, let's say, reinforcement learning algorithms.
Mhm.
But if you really want broad generalization out of it, like they can't be all in the same room. So you really need to get much better coverage of the world.
Right.
And by aggregating data from robots in many different sites, now you can get much better coverage. Now, this is still a prototype for what might be a larger system, because these are still data sets collected by researchers essentially doing science experiments, right? So you could imagine that in the future, the aggregation wouldn't be across different research labs, it would be across different deployed robots. Now, that, of course, is a much more complex undertaking. That requires more than just science. It also requires some kind of organizational effort, consensus from companies, and so on. But that, I think, is kind of the real thing once that comes about. And you could imagine a future where the data streams from a variety of different deployed robots in lots of locations are agglomerated and then used to train one centralized robotic brain, which can then be handed back to these robots to improve their performance. And
Right.
the key thing that we want to de-risk with this project is just, if you do this at any scale, even at the scale of academic labs, can you even get a policy that can drive all the different robots? Because if that's not possible, then aggregating heterogeneous data wouldn't work, and we would need to somehow figure out standardization. Standardization is hard. So what we know now is that we don't have to worry as much about standardization.
Yeah,
We should just worry
because
about scale.
yeah, this model, then the weights are being passed around and they're controlling different form function robots, right? I mean, or were they all just variations
So
of a
in these
robotic
experiments, the
arm?
robots were all arms with parallel jaw grippers. We are
Mhm.
right now experimenting with generalization across single arm and bimanual systems. Uh, at some point in the future, we'll also look at multi-fingered systems, things like that. So far, truth in advertising, it's one arm with a parallel jaw gripper. They're just different brands of arms. Now, they do vary a lot. So the small scale kind of hobbyist Widow X arm is like, maybe 50 centimeters long, kind of smaller with a weak gripper. The big, UR10 robot is an industrial robot meant for manufacturing, quite a bit bigger, beefier, has a stronger motors, stronger gripper, that sort of thing. So there's variability. They're still the same sort.
Right. And the model that you're training on this aggregated data, is that the reinforcement? Can you describe that
Yeah,
model?
we actually trained two models. One was based on the RT1 model,
Mhm.
which was developed at Google last year. And the RT1 model is basically it's a transformer that reads in language instruction commands, an image, and then it outputs discretized tokenized actions. So it's kind of almost like the most obvious way to design a transformer based policy. The second model was the RT2 model, which is a more recent development, which actually uses a backbone from a pre-trained vision language model. So vision language models are trained to look at images and output responses to textual questions. So you give it a picture and you say, like, is there a dog in the picture? And it will produce some text to answer that. And then we took this vision language pre-trained backbone and then further fine-tuned on robot data to output robot actions in response to robot observations. So you can sort of think of, like, the VLM has a number of tasks that it can do. It can answer questions, it can produce captions. Now there's one more task, which is given a robot instruction, output the actions for the robot. And now that's a much more powerful model because it has all that internet knowledge baked into it from the vision language model pre-training. And that's the one that we used for the more complex queries with spatial relations and things like that.
Yeah. Is most of your work on the data side or on the model side?
Well, it's really both. And to some extent, they also go hand in hand because depending on what your algorithms are able to handle, that will inform the kind of data that you need to get. For example, a lot of the more algorithmic work that my lab does these days is concerned with techniques for offline reinforcement learning. Offline reinforcement learning is basically a way to take data and produce more optimal policies. So imitation learning methods they take in data and they produce policies that reproduce the behavior in the data. Offline RL methods take in data and attempt to produce behaviors that are better than the average behavior in the data. So intuitively, you can think of it as using the data to figure out what options are available to you and then selecting the best among those options. In fact, methods that use world models, as we discussed before, can be seen as offline RL methods because typically the way they work is they train the world model on existing data and then they use it to extract better control strategies than the typical thing that was demonstrated in the data set. But there are also other ways to build offline RL techniques that don't rely on world models, that rely on value functions and things like that.
Where do you think the research is heading? Because everything's moving so fast. Is there for robotic control? Do you think that the research will settle on one architecture and then there will be different flavors of that architecture, but everyone will agree, yes, that this is the best way, and then it's a matter of training, generalizing across robots and networking data? Or do you think that there will be a series of models that will be used for various functions?
Yeah, good question. So I'll give you an answer. It's a slightly aspirational answer. So maybe this is more like where I wish things were headed. I don't know if this is necessarily where things will head, but I think it's very important for robotics to kind of adopt a paradigm where we are in the habit of having reusable models where just like in computer vision and NLP, if a researcher produces a good model, other robotics researchers should be able to use it. Now, that might seem like a very obvious thing, but this is not actually how robotics works today. Most robotic learning research, the artifact that is produced is not actually the model, it's the code or the paper or the insights. The models themselves are almost never portable, never mind across labs, like even across different locations in the same lab, different times of day in the same lab, that sort of thing. And I think we really need to move that towards a setting where we have models that are trained on data sets that enable generalization across different locations and systems, different objects, that sort of thing, that we can then give to other researchers, other practitioners that will also run on their systems. And once we've got a good flow for doing that, maybe using things like this RTX data set that has multiple robots, maybe using some other data set, but something where we can just get in the habit of doing that, then we can actually make more progress as a community towards shared generalizable systems. Now, until that happens, there's absolutely no question about whether people will use the same architecture or the same model. Like if they can't even share anything across, then that won't work. But once we can share something, and probably the key to that is a data set that enables that, then the community can figure it out. Like maybe at that point, perhaps it'll be realistic to have a single pre-trained backbone that, like the llama model in natural language processing, an analog to that in robotics, and then people can build on top of that. Or maybe there will be several such things. Maybe there will be a few big ones that kind of the big, well-equipped labs produce that others will then build on. But before we get to any of that, we need to just get in the habit of actually building models that others can run.
The other side to robotics is just the hardware. And I was talking to a guy the other day who was talking about where robotic control systems are heading, and he's not a roboticist or an AI researcher, but he was waxing very optimistic about there being household robots within 3 to 5 years, and that sounded unlikely to me because just the hardware alone is not, at least the hardware that I've seen, is nowhere near being able to do releasing it into an unstructured environment full of randomness. Do you think that the hardware is moving along with the AI, or is it lagging?
That's a good question. I think that a very important part of that question is just what kind of hardware we need. Um, I think to a large extent, learning methods should actually lower the bar for the hardware that's necessary. Um, Basically, the exercise you can do is you can get one of these like little trash picker devices and see what kind of tasks you can do around the house with it. I mean, obviously it's very limiting, so there's some things you couldn't do, but there's also a lot of things you could do with it. Certainly, you can tidy up the floor, put things in different locations in the kitchen. It's actually kind of surprising how much a relatively primitive robotic system can accomplish. So there's very nice work out of Professor Chelsea Finn's group that I also helped with a little bit by a student named Tony Zhao, who developed a bimanual robotic system out of two low-cost robots from Trusson Robotics. So these are not even like the fancy industrial arms. These are basically very fancy hobbyist robots. So they cost about, I think, $5,000 each. And most of his kind of cleverness in his research was in devising a very convenient teleoperation system, a teleoperation rig that he could hold with his hands and control this fairly cheap bimanual system. And you could demonstrate all sorts of very complex behaviors. You get this thing to like put a shoe on a foot, use tape to tape down a box, things like that. And the learning methodology that could produce the autonomous policy was well designed, but not particularly profound. It sort of used state-of-the-art transformer-based techniques, but didn't really have any particularly like surprising innovation. The key to it was really building a really good teleoperation rig that allowed him to produce those behaviors, and then very high-quality engineering to then get that down to a policy. So this is called the Aloha system. For those who are listening, I'd encourage you to check it out. And it probably gives some idea of what even very primitive hardware is capable of if it's equipped with the right data, the right kind of teleoperation rig to provide that data, and kind of good bread and butter modern machine learning techniques. Now, that's still not going to do everything around the house, but I suspect that for folks that watch these Aloha videos, it'll kind of maybe slightly change their mind in terms of the kind of hardware we really need for everyday tasks. So probably there is still some innovation, but it might be actually like less than you think.
That's interesting. And then the controller side, the AI side, the model side is it. I mean, if that is adequate, that hardware, how much more improvement is needed on the control side?
That's a complex question because that's probably very heavily dependent on the required bar for robustness and the degree of generalization. So in some ways that sort of parallels the autonomous driving story, right? Like if you wanted to build an autonomous car that could succeed in like 90% of cases, well, that's probably something that we've had for over a decade. But if we want an autonomous car that'll succeed, that'll avoid catastrophic failures with enough robustness that you could just deploy it on any road in any city, just dealing with all those tail cases, that's still an open problem. And I think with home robots, it's going to be the same way, that if you want to lop off the bulk of the things and the bulk of the situations, maybe that's not quite there yet, but I think that it's reasonable to imagine that we get there soon. But how long it takes to get that long tail fully figured out, that's a much more complex question. I think that one thing that's pretty interesting is the degree to which vision language models have progressed over the last, really over just like the last 12 months. And that's especially relevant for robotics because while the way that vision language models are typically used is more for kind of traditional perception tasks, question answering, that sort of thing, the ability to reason about visual observations, perform inferences about spatial arrangements of objects, that sort of thing, that is something that is likely to translate into better robotic capability. And because generalization is one of those big challenges, I mentioned, this long tail issue, I think there is a lot of reason to be optimistic about the potential for those models to eventually improve the robustness of robotic controllers as well.
People are talking about combining language and vision, or I should say language and world models into agents that can reason, plan, and take action. That sounded to me very much like robotic control. I guess what I'm asking is that research and the people who are in robotic control research on different tracks?
The answer is a little bit complicated, but maybe the short version is that yes, it's closely related to a lot of robotics problems. In fact, there's plenty of work in robotics on using language models for essentially constructing plans and then connecting those plans up to some kind of control mechanism that can bring them about. Now, probably this stuff started maybe like roughly 2 years ago. Probably one of the more well-known works in this area is the SEICAN paper from Google, which used a language model to plan long horizon behaviors for robots. Initially in this field, one of the big challenges that people were concerned about is how to connect up the language model to perception and action. Because standard language models have to operate on symbolic representations of the world, so you have to take those symbolic representations and somehow weld them onto rich sensory perception and complex actuation. Now, initially, the way that this was done was kind of along the lines of what you described, by trying to construct some sort of a joint planning procedure that would figure out both a probable sequence of symbolic steps, essentially language, and the corresponding behaviors that would bring that about. There's actually a paper from one of my colleagues called Grounded Decoding, which proposes a Bayesian filtering approach to doing exactly that. That said, something that we've seen over the last maybe like 6 to 9 months is that increasingly, with vision language models becoming more powerful, a very appealing alternative, instead of doing this, is to actually train models end to end to solve the entire problem. Now, those models can still be doing planning. If you have a vision language model that outputs text and also outputs actions, you can do essentially the analog of chain of thought prompting. You can tell it, okay, here's some complex problem, and produce steps for solving that problem. And then once you've produced those steps, then produce the actions. And that works. So you could tell a robot, okay, like make breakfast, and we'll say, okay, to make breakfast, I need to do this and this and this. And then for the first step of that, it'll try to output the actions. So that's a viable way to use vision language models. But then it's still, you would still end up with one model that does that. And that's very desirable, because if you have one model, then you don't need to deal with this problem of trying to somehow stuff visual observations into a symbolic representation to then pass it into the language model. Basically, instead of designing that interface by hand, it emerges naturally through joint training of the whole thing. So this is actually the principle in which the RT2 model works. And one of the examples there that illustrates this kind of chain of thought style approach is we asked it, we wanted to intentionally construct a scene where the correct behavior is a little bit non-obvious. So we had a scene that had some common household items and had some tools, the wrong kind of tool. So it's supposed to hammer in a nail. There's no hammer, but there's a rock. And we ask it, okay, you need to hammer in the nail. What should you do? And then it figures out that it should pick up the rock. It actually says rocks, and then it goes and executes the corresponding actions. So now that's very primitive planning, right? So it's kind of more semantic inference than planning. But these things are in their infancy. I think they'll progress a lot more over the next few years.
Do you in the last 5 years, which is about the time I think since I spoke to you, has the progress in your field specifically mirrored the progress in generative AI?
I think that progress in robotics always does tend to lag behind everything else, because when we figure out effective learning techniques, then it's always a longer journey to go from kind of conceptual method to small scale prototype to larger scale prototype. Because with generative models, well, you can harvest lots and lots of data off the web, so the lag between developing a method and then scaling it up to internet scale data is typically relatively short. With robots, that's usually not the case. So while certainly modern advances in generative modeling have made a big impact on robotics, and there's particular very interesting adaptations of those techniques that combine it with reinforcement learning planning and so on, I would say that so far we have a lot of good indications of the potential for these things, but we don't have the kind of large-scale prototypes that have been produced, for example, for diffusion models, for image generation, or for language models. And I think the key there is actually getting these kinds of reusable models with large and diverse data sets that would make it possible for us to produce these larger prototypes.
Yeah. So what's next in your lab?
Yeah, so one of the things we would like to do is provide the community with pre-trained models, now that we actually have a data set to work with, that can be easily adapted to a variety of downstream applications. So not just a model that can do anything, and that's maybe too ambitious of a goal, but at least a model that can be adapted to do anything. So if you could imagine, let's say, a model that is pre-trained to take in language, take in maybe goal observations, other forms of commands, and produce outputs for a variety of different robot embodiments, not with the goal necessarily of solving every problem, but providing a really good initialization so that somebody that has a particular specific robotic system with a particular desired formulation of their task, a particular objective, they could take this and with a much more modest amount of data adapt it to their problem. And I think that now that we actually have good multi-robot data sets and fairly mature techniques in terms of how to train models with variable inputs and outputs, we're actually just about ready to do that. So our first prototype for this should be coming out very soon. But it's just going to be the first step. From there, a lot of what we have to investigate is what does that the life cycle of such a system actually look like? What are the right techniques for efficiently fine-tuning robotic foundation models to particular domains, to different morphologies, different commands, and so on? And there's probably actually a lot of interesting questions to be answered there. For example, robots can collect data autonomously. So could you, for example, have an autonomous fine-tuning procedure based off of one of these pre-trained models? Could you have a fine-tuning procedure that respects safety constraints, things like that? So there's a lot of interesting questions that we could answer once we have that base model all set up.
There's a lot of people I've been talking to about the proprietary open source debate with regard to generative AI. In robotics, is there an analogous situation where there are enterprises that have tremendous resources? I mean, the robotics are not as compute intensive, the models that you're talking about. Is that right? And so is it more equal, like what's happening in industry and what's happening in research?
It's complicated. So certainly compute constraints are an issue, right? Especially once we go into vision language models. The most effective vision language models are actually the largest models out there. So the largest version of the RT2 model, for example, is 500 billion parameters. So very much in the same ballpark as the largest models out there. Of course, you can do a lot of experiments at much smaller scale, and that does make it somewhat more accessible. In terms of data, it's kind of interesting. Like there are definitely companies that have large numbers of robots deployed.
Mhm.
Those are not necessarily the companies that have the most interesting data, though, because if they're deployed in like a warehouse, it's mostly
Right.
grasping of items, and maybe in some ways the open data from researchers is actually more interesting. The picture changes somewhat if you go into mobility, things like autonomous driving. Like, yeah, there's going to be big industrial players with their own proprietary stuff. But even there, like, data sets constructed from dashboard mounted cameras that are out there now are actually very large. Certainly not as large as what Tesla or Waymo has, but substantial. So I think you're right that some of the proprietary advantage is not as large. But it's kind of maybe the more pessimistic take on it is that it's because no one has the data, so the companies don't have the data because no one does.
The control of an autonomous vehicle and the control of a robot arm or some other form factor are they different fields? I mean, when you're working on these models, are you thinking also about their application in autonomous vehicles?
Yeah. So traditionally, these are extremely different problems. But what we're increasingly seeing is a degree of consolidation in the sense that very similar building blocks can be reused. So I think actual autonomous driving is maybe one of the tougher things because of all the constraints and regulations and all that stuff. But for small scale mobile robots, think like drones, sidewalk robots, etc., we already have research projects where we've developed vision-based navigation policies for these things. They use essentially the same exact architecture as what we use for the robotic manipulation problems. And a very natural next step is to actually combine, not just have the same architecture, but literally the same model. In principle, at this point, there isn't really any technological obstacle to doing that. Now, of course, there's a lot more to driving, let's say, an autonomous car than just avoiding obstacles and reaching the destination. You have to put in a lot more knowledge, constraints, all this other stuff, and that probably is rather specialized. But my hypothesis is that we'll probably actually see a lot of consolidation around the same basic building blocks for the core kind of perception action kind of system within these things. And then maybe where they would differ is the kind of planning layer that sits on top of that and then directs it in terms of what to actually do in a given situation.
In your work, there is a pull for academics because of the compute constraints and money, salary, and that sort of thing, to pull people into the industry. Are you working straddling academia and industry, or are you
Yeah,
firmly
so
in?
so so I spend 20% of my time working with
That's what you
Google
said. Yeah.
DeepMind. I think that in terms of the degree to which an industry research versus academic research in robotics is more or less appealing or progressive, I think probably it's a little more I would say tilted towards academia than, for example, natural language processing or vision, and maybe in part it's because um, there are a lot more of the kind of big questions to figure out before things are actually have revenue, so to speak. Like
Yeah.
you could build a language model or vision system that provides an actual business case today, whereas the analog and robotics is probably still a few years out. Um, that said, I do think that it's there's a lot of rapid progress, and certainly a lot of students from my group are excited about starting companies based on technologies they're developing and things like that.
Yeah.
So I think we'll see that kind of catching up in the near future.
Yeah. And you think that this is the year that AI kind of hit the public sphere, and people confuse robotics with AI all the time. Will the day come? I mean, obviously the day will come, but when do you think the day will come that there will be some uh, commercial application or open source application that is adopted in by the public, that people will suddenly
Mhm.
be talking about robots as opposed to AI?
Yeah, that's a complex question because I think that um, if I had to guess, I would guess that a lot of what's needed beyond the core technologies is a pretty substantial upfront investment to sort of overcome the activation energy to get something like that to be practical. And that's not too unprecedented in the sense that, like, more or less the same thing happened with language models, right? Like the core technology for like next token prediction is pretty old. What was needed to develop uh, the kinds of technologies and products that really capture the public imagination is a large investment of effort into engineering them really, really well, and curating, collecting, and assembling the right data sets to get them to work really well for like a thing that basically anybody could grab and use. That's partly there's a scientific question there, but a lot of it is really sort of organizational, economics kind of questions. And the trouble with those things is that I think they're hard to predict because they have more to do with like the point in time at which people decide that it's time to lay out those big resources to make it happen, rather than just predicting when the technology will evolve. So the technology might evolve steadily, but then the inflection is really the resource allocation. So I don't know. I can't predict when that would happen. If I had to bet, my bet would be like closer to 5 years than to 10, but I'm not sure.
There's been this this threat debate has created a lot of acrimony in the community. Do you have a view on that, or is your territory removed enough that you don't engage in that?
Yeah, it's a complicated question. I mean, I tend not to prefer uh, not to get too much into discussions like that. Um, Partly because I'm not really sure exactly how things will go, and I think that partly, perhaps as a roboticist, I maybe tend to be a little more pessimistic about where we're at in terms of overall like AI systems. Like, kind of hard to imagine that an AI system that can't control a robot to do basic things that are easy for humans would be all that capable overall. But this stuff is hard to predict, and I think that maybe like the one constant in AI research is that people are continually surprised by the things that turn out to be easier than imagined, and also things that turn out to be a lot harder than imagined. Right. So if you go back a couple of decades, it would be pretty shocking to think that, for example, artists and writers would feel threatened by AI systems long before, like, the gardeners and cleaners would. But that is the world that we live in today, and maybe that tells us to be a little humble about our predictions.
Yeah, yeah, that's right. And the governments around the world are very focused on regulation of generative AI specifically. Is there regulation? Are governments looking at robotics or AI and robotics in the same way? And is there government support. There's been a lot of talk about providing compute resources to research and smaller companies so that that's not held within these big tech companies. Is there that kind of talk in robotics that the government should or could provide more resources to accelerate
Yeah,
research?
there's certainly plenty of talk about that. It's typically not, from what I've seen, not something that sort of tends to separate out robotics versus AI versus other things. There's certainly talk about it. I haven't seen a great deal of action yet, but I imagine it's something that moves slowly. So yeah, I don't think I would say anything differently than any other AI researcher in that respect. And I don't think that from what I've seen so far, there's anything that kind of treats robotics in a particularly special way in that regard. But yes, this is a big issue, and it's probably something that we, certainly in the United States, we need to think carefully about how we're going to maintain our technological edge and how we're going to allocate the resources that are necessary for that.
And that leads me to another question, because I spent a lot of my life in China. Where is China in this research? Do you think they're ahead, behind?
I'm not sure exactly. I mean, one thing I will say is that I think that researchers from China, from Chinese universities, have been very successful across all areas of AI, including robotics, and certainly a lot of really interesting research, increasingly I do see coming out of China. For example, when we were doing a lot of our data set collection work, we were actually very surprised to learn in the middle of it that there was a really amazing data set that was released by some researchers from Shanghai that was comparable in size and scope and diversity to the one that we were collecting, and that was wonderful. They released it open source. I talked to them on the phone. They had really interesting thoughts about what they wanted to use it for. So I am seeing a lot of kind of uptick in terms of the quality and the kind of results that are coming out. The other interesting thing is that actually a surprising number of advances in hardware have actually been enabled by companies out of China. For example, one of the most widely used platforms for quadrupedal locomotion research is produced by a company called Unitree from China. And I think a lot of the things that make that platform so appealing are that, it's relatively simple, it's affordable, and it's designed in a way that makes it easy for researchers to get kind of into the guts of it. And that also, in my opinion, has actually been a very good thing, because while we might be concerned about competition and all that, in the end, it's actually accelerating research here in the United States. So that's what I've seen so far. I mean, without trying to make any value judgments on what's good or bad, it seems like there's a lot going on.
That's it for this episode. I want to thank Sergey for his time. If you want to read a transcript of today's conversation, you can find one on our website, Ion AI. That's EYE-ON.AI. In the meantime, remember, the singularity may not be near, but AI is changing your world. So pay attention.